Recall this week that we did a reaction between magnesium and hydrochloric acid. You all used Lego pieces to represent that reaction. And we have our chlorines, these red ones with the satellite tops, attached to our hydrogens down here and our magnesium block here. And in this reaction, we could model that the hydrogens would detach from the chlorines and they would attach to the magnesium to make a compound. And recall that magnesium has a valence of 2, 2 spots, and chlorine has a valence of 1, and it can bond to chlorine in a ratio of 2 chlorines to 1 magnesium. In doing so, all the valence are filled, all the places for bonds are filled, and all of the elements are satisfied in how many bonds they're making. There's no open spots anywhere. So as I just showed you, magnesium combines with chlorine in a 1-to-2 ratio, meaning that for every 1 magnesium, there needs to be 2 chloride ions. The ratio of elements in a compound, so this is our compound magnesium chloride, is determined by the valence of those bonding elements. So the valence of magnesium and the valence of chlorine determines the ratio that they are bound together. Valency is the combining power of the elements. It determines the number of bonds that an element can make to another one. So therefore, if you know the valence of an element, you can know what ratio it will combine with other elements. Luckily for us, elements' valence follows a pattern. And this is a pattern that we can see on the periodic table. So here's our periodic table. You can see that there are element symbols on here. The element symbols tell us what the element is. So for instance, Li is representative of lithium. Na is representative of sodium. Mg, which we've seen, is representative of magnesium, and so on and so forth. The symbols help chemists write things in shorthand. So instead of writing out all of the words, we can just use the symbol and we know what that element is. In addition to the element symbols and the element names on our periodic tables, we can also see some numbers above each of the columns. The numbers above the columns represent the possible charges for our elements, meaning everything that falls in this first column can have a charge of 0 or +1. The +1 is representative of the valence, meaning that everything in this column has a valence of 1. We can also see for the second column that the number is 0 or +2, meaning that everything in this second column has a valence of 2. This middle section doesn't have charges above it like the other columns do. This middle section is special. But if we go over to this side here, we'll see the charges continue at 0 or +3, and moving on from that, we can see here that the charge turns negative with a -3, but the valence is still 3. And same for the next column over, 0 or -2, the valence is still 2. These ones can make 2 bonds. These ones need to make 3 bonds. And this column here, where the charge is 0 or -1, the valence is still 1, meaning it can make 1 bond. So the charges on the periodic table follow a trend, and they determine the valence of the elements that are underneath it in the column. So now let's look at some specific examples where we look at the charge and the valence for that element. We'll start with our positively charged elements here. As we saw in the periodic table, sodium can have a charge of 0 or +1. So when sodium is in the +1 state, it has a valence of 1. And we're going to represent that with this piece here. And it has 1 peg in which it can make a bond. So 1 peg means 1 valence, 1 bond, and it doesn't have a cap on it, meaning that it's a positive ion. Calcium has a charge of +2, and so you might be able to guess from that that it has a valence of 2. So for calcium, we're going to use our little black blocks here. And these are representative of calcium because they've got 2 spots to make bonds, so 2 valence spots, as well as it has the positive nodes that can make the bonds. So this is what we're representing for our Legos. And the last one, aluminum, has a +3 charge, so it also has a valence of +3. So you can see that it's following a trend here. We're going to represent our aluminum with this gray piece that has 1, 2, 3 open spots, meaning it has 3 valence, and it can make 3 bonds here. So these are our positive ions, and we can look at the other side. So first we'll look at fluorine. First let's look at fluorine. On the periodic table, it can have a charge of 0 or -1, and when it's in its -1 state, it gets this special ending, fluoride. And as you may be able to accurately predict, if it has a -1 charge, that means it has a valence of 1. So we'll represent that with this piece here. You'll notice that this piece is for a negative ion, for a negatively charged element or atom, because there's no spot to make a bond on the top. It can only connect to something else, and it can only do it once. So there's one space here for it to make one connection, one valence. And then oxide, which is a derivative of oxygen. So oxygen can have a charge of 0 or -2, and when it's -2, it gets the same ending, the "ide" ending, and becomes oxide. And you may be able to predict that a -2 charge means that it has 2 valence. And we're going to represent that with this piece here. And you can again see that because it's negative, I have covered up the top pegs, so it can only make bonds on the bottom, and there's room for 2. 1, 2 places for bonds. These are the Lego pieces that represent my different elements in their charged state. So the really wonderful thing about the Legos is that it can help us predict in what ratio our elements are going to bond together based on their valence. So 1, 2, 3, and 1, 2. So if I wanted to make sodium fluoride, which would be these 2 pieces here, so I have sodium and fluoride. I've got 1 spot open that sodium can make a bond, 1 valence. And fluoride has 1 spot open here, so these will go together in a 1-to-1 ratio, like so. And so when we're writing our 1-to-1 ratio, I've attached 1 sodium, so I use the symbol Na, and I put that first, and then fluoride, which is an F symbol, and I've only used 1 of those. These go together 1-to-1 because 1 valence on each of them means they each need 1 bond to satisfy their valence. Let's say I had calcium and some fluorine. So 1 fluorine has 1 open spot here, and I can bond to 1 open spot in the calcium. But you'll notice there's still a peg open here. Elements will never have open pegs, so they always need to be filled up. So that means I need another fluoride ion, and I'll put it on here. And therefore, the ratio is 2-to-1, because fluoride has a valence of 1, so it can only make 1 bond. But my calcium needs 2 bonds to satisfy its valence here. So I have to attach 2. 1, 2. So if I write that, that would be calcium, Ca is the symbols for that, and fluorine, F. But now I need a little subscript of 2 to denote, to represent that I've got 2 fluorines attached to it. Let's say we were looking at calcium and oxygen. So you'll notice that on the top of calcium there are 2 valence, it's got 2 open spots, and the bottom of oxygen also has 2 open spots. So when the valence number is the same, 2 and 2, They go together in a 1-to-1 ratio, 1 calcium, 1 oxygen, and both are satisfied. There are no open slots on either piece. They both have their valence filled. So calcium, CaO. So when the valence is the same, 2 and 2, it's just a 1-to-1 ratio. So let's do something a little bit more complex. Let's say we have aluminum, which is represented by this 3-pegged piece because it has a valence of 3, and I wanted to bond it to oxygen, which has 2 open spots. Why don't you go ahead and try and make a prediction as to what the ratio will be of aluminum to oxygen. So do that now. The Lego pieces are really useful because when we start putting them together, we can build the ratio that these atoms have to have. If I just do a 1-to-1 ratio and I attach my aluminum to my oxygen here, like so, you'll notice there's a problem. There's one open aluminum peg, and that cannot be. There cannot be open spots. So in order to satisfy that, I have to add another oxygen because that's all I have. All I have is oxygen and all I have is aluminum. I have a lot of them, but that's all I have. I can't add something with a 1 in. So if I attach it here where there's an open spot, you'll notice now there's another open spot on oxygen, which again is a no-no. No open spots. So I will add another aluminum. Add one more. But now you notice there are 2 open spots on the top of aluminum. Again, no, no, no. So I have to add one more oxygen, which will perfectly bond with those 2 open spots. And now all of the bonding spots are filled. Everybody is satisfied. So if I write out my symbol representation, I had 2 aluminums, 1, 2, and 1, 2, 3 oxygens. Aluminum oxide, and that's how you would write that.